You for coming. All right, so we're going to start off taking a look at other types of counters. Let me just do a kind of a quick review of what we've had so far. So we talked last time, asynchronous counters, if you remember, we could pretty easily design a system that each time that the last stage kind of flips around, that it sends a bit pulse. So when I'm counting up, when I go from a 1 to a 0, that basically shows that that digit has rolled over, which means the next one up has to be able to count it. So you can, one of the ways to think about this is you kind of think of your hands, and if I treat each one as a bit, I can actually count up to 1,023, right? 0, 1, 2, it's kind of awkward, right? And I've got 3, and then you go to 4, right? 5, 6, right? And every time I hit them, 7, when this last digit flips, boom, I go to 8, it triggers the next bit. So going from a 1 to a 0 triggers the next bit up to go down. And that works fairly nicely, but by the time you get to the last one, right, when you're like, all the way up at on, and that, this bit triggers down to trigger the final bit to turn on, there's a lot of latency as the signal kind of carries through. As you get bigger and bigger numbers of digits in there, it will actually take a while to kind of have that transpire. That's one of the challenges that goes on. If it gets too long, it can actually take so long for them that I can get glitches and all kinds of other stuff. We don't get the protection that you would normally get inside of a circuit, so you better make sure you design it. It's really easy for them to kind of get these runs that they feed back in. So you've got to make them safely operate. So that was one of the problems with asynchronous. We solved that problem by going to a synchronous system, but now we have to design a little more carefully so that every bit updates within that time period. We found a fairly easy way to do that, but we commented if that latency gets, as long basically as our time period to solve them, and really you want it to be less than half the clock time period. If it takes longer than half the clock time period to calculate the next update to the bit, you're going to have to kind of subdivide your clock. So this is why we often don't just build one gigantic clock. We'll build clocks that'll get it to different time scales on here. That way we can kind of cascade them together. And we talked a little bit also on some of the problems in the lab that were happening. And if you remember, the big thing from that is um, on FPGAs, you cannot cascade logic into a timing network. Timing networks are kept separate. Those have to be defined. So today we're going to talk about two new types of counters as one of our kind of big things, then we'll talk about some strategies to build. So the first new counter we're going to have is called a ring counter. Now, I have mentioned this one before. A ring counter is particularly useful if you're using what's called one hot as your system of labeling. Remember when we talked about labeling states? Let's say I have whatever, A, B, C, D, E, 5 states here. That would take me at least 3 bits in binary. So I could label these in binary, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. This would be a binary system. A one hot system actually looks at this and says, hey, look, this is 3 bits. If I were to just assign 1 bit to each state, right? So I make 0, 0, 0, 0, 1. This is kind of my A state, my B, C, D, E, right? So I can say 1, right? The B is on if I'm in B, C is on if I'm in C, D is on if I'm in D, and E is on if I'm in E. I never allow 2 states to be on, 2 of these bits to be on. So only one of these is active at a time. Then it's only one's active. That's where the name one hot comes from. Now, this type of one hot you know, we look at it's actually really easy to design. That's kind of the preferred method for FPGAs to kind of build automatically. It's very easy for them to be safe on these type of things. You know, they don't have to worry about timing issues because when I'm having multiple bits turn on and off, like here, I've got to turn one on, turn one off. I've got two bits going. I have to hope they transition at the same time, which means that I better make sure this transition happens within a clock area. Here I've got three transitioning, right? One on and two off to go from D to E. That means all of these bits have to be inside the same clock domain on my chip. Um, and so that can create timing issues. For something small like this, you're pretty much guaranteed, yeah, it'll be fine. But when you get to larger numbers, it gets more and more challenging to make that happen. So if you get really big designs, or if that design happens to cross a clock boundary, sometimes you have to cross that clock boundary because your system is actually deliberately has to stand between. Maybe you've got one area that's running on a fast clock and one that's running on a slow clock, and you have to have this state machine that operates between the two. So I might be forced to be on a clock boundary, and then I have to be very careful to do the checking, and even assertion checking becomes really difficult under those cases. This is a little bit easier to handle because I only have one on. So if I'm doing a transition, I can turn B on and then turn A off. And I know in the in-between when they're both on, that's not a legal state to be in. So I know that's part of a transition, so I can reject the errors on it and continue through. I'll only use it when only one is on. Well, the question then is, imagine that I'm doing a counter with my states. A, B, C, D, E, and I'm doing kind of a counter setup where I count between my states. Right? So I've got a mod 5 counter that's going on. Something small like this, I could decide, hey, I'll just use one hot. And then to actually count on these, I don't have to use a regular adder or anything to do it. This, in order to go from A to B, is I just have to shift. I don't even have to do that turn one on, turn one off thing. I can actually just set up what's called a ring counter. And a ring counter, I'm going to erase this because I think it's fairly obvious. What a ring counter does is I take and I set my D flip-flops, and I just hook them to be able to count. And then I feed them back. So let's say this is the one that holds A, and this one holds B, this holds C, D, and E. Now, this is a D flip-flop. Actually, all of them are. And so if this is a 1 and these are all zeros, to count to the next state, all I have to do is shift right. So, and we talked about how we can make a shift right and a shift left on a previous class. I think it was actually 2 ago for these serial registers. But all I have to do for this clock is just hook it around. That's called a circulant setup. And that's where the name ring comes from, because it just hooks the output of a shift register back into its input. And so if I give it the command to shift right, all it'll do is this one will shift over to here, the zero shifts, that zero comes around. So you'll see the zero comes around, the one shifts, and all the zeros shift down. And so it does exactly that count. It goes from A to B. No chance for an error, no weird intermediate states. They're all hooked on the same clock, and I just tell them shift, and they go. So it makes a very easy, safe counter for this kind of one hot setup. So this is a really good setup for one hot. Very safe, very easy to build. Has a lot of nice features. 1 bit per state. So your only challenge is if you have a huge number of states. this can get a little bit cumbersome. Usually you end up with a large number of states on things like computer design. So one of the classes you will take after this is Comp Org. And Comp Org, you'll actually build a kind of downsized, a simplified version of a 32-bit processor. It sounds really intimidating. It's surprisingly not. We break it into little pieces. But there is this kind of, if you dealt with all the possible commands that were out there, you'd have a huge number of states. We're going to break it down in intelligent ways to simplify it. Um, and we'll have different stages that will handle things, get an instruction for me. We call this fetch, figure out what the instruction is. We call this decode. I actually process the instruction. We call it execute, access memory to get data for me. Right, that's the mem stage. And then there's what's called write back, where you kind of resolve the answers and store it in the temporary storage area. That's your register file. So there's 5 stages. So we'll have a 5-stage, that's called a 5-stage pipeline. We'll have an exact counter that works like this. As the instruction goes through, get the instruction, decode the instruction, do the instruction, access memory, and store the results in your register file. It'll walk through that kind of sequence over and over and over again. And then inside each one of these, when you decode it, you'll split to different states depending on what the command is. And we'll show different ways we can handle this. If you drew it out in all of its glory, goodness, and built it in one big swoop, you'd have a giant number of states, easily thousands of them for different commands. But you can also break them up into smaller, which makes it easier. So this fits nicely for that type of sequence as long as you break them up. Worst case scenario would be a huge number like that if you did all the instructions on them separately. We'll often label the instructions by, hey, this is an add command, so the add command's execute phase, so on and so forth. But it's even easier if you kind of group them into these pipeline areas and work from them. So my basic point on this is that a ring counter is very nice for one hot. One hot is very good for implementing kind of these different stages, as long as you don't get too many of them. And if you do get too many of them, look for ways you can kind of break them up, because one hot is a very good way to do designs. Okay, it's a very simple counter to build, so there's not a lot to this other than understanding its use for it. It's obvious as you keep shifting, it'll walk through it. I can do count up is a shift right. So shift right circulant is the technical name because it goes circles around. Counting down is shift left circulant. You go the opposite direction and it circles around the other way. You'll get to these commands when you do assembly language, because these are standard assembly language commands, but this is the hardware implementation of it also. So if you ever see any of those ones where you do a shift right, you'll see these circulant ones. If it's not coming around, then it'll be another type of shift right or shift left. There's also logical and arithmetic that's used. Logical always inserts a 0. So the whatever is the new thing coming into fill will always be 0. That's called a logical shift. Arithmetic shift is if I am shifting to the left, it's the same arithmetically as logically. If I'm shifting to the right, it's not. Arithmetic is basically handling 2's complement. So whatever the most significant bit is on an arithmetic shift, it'll shift over, but it'll also stay there. So if there's a 0 here, there'll still be a 0 here and shift, but that's called an arithmetic. So those are the full types of shifts. For our system on a ring counter, it's only circulant though. I mentioned the others just for completeness. And when you get to those, you'll know what to do with them. All right. Do we feel good with the idea of a ring counter? I guess one final thing I could say, if you wanted to take a look at this and have some operation like, maybe in states A and C, I wanted to output a 1 for whatever reason, right? If I had to do that, to figure out what state I'm in, all I have to do is I just take this line and I tap into it. Since this is state A, this one will right here, this wire will be a 1 if I'm in state A. And this is the output from the register that holds state C. So if there's a 1 here, I'll be in state C. Since there's only one 1, it'll only be in one location. So I can then take this and do that. So if I wanted a 1 output when I was in state A or state C, this is the way I can do the output. So you can see it's actually really nice to calculate outputs. Remember, when you're doing any of these type of register transfer level things, that's on, right? Shifting from one register to the next, there's basically 3 types of building blocks. There's the memory, there's the thing that does the transition between states, and then there's the output logic. Those are the 3 basic chunks of anything that does register transfer level. All right. That's a ring counter. Now, a lot of people look at this. I'm going to erase the output for a sec. A lot of people looked at these and said, hey, a ring counter, it's pretty good, but it's not the most efficient on using registers, right? Because I have to have 1 per state. What if I took that same basic idea and I did a slight variant on this? Instead of taking the output from Q, what if I took it from Q prime? All these other ones are Q to D, except the last one, which does Q prime and comes back around. You can also think of it as taking it from Q and putting in an inverter in the line. Now, if I do that, it's basically a ring counter, but there's this inversion in the system. Now, we'll start at all zeros because I'll generate 1s from this inverse that's coming in. This ring is no longer called a ring counter. It goes back to the last name of the person who invents it, a Johnson counter. Johnson counters are no longer for 1 hot because it's not going to just generate 1 hot. So we start, our first thing of a Johnson counter is all zeros. I'll do it for 5 because that's what I've got here. So this is kind of my 0 state. When I count, I'll do a shift. So I'll do that same shift right in here. All the zeros will move over. The last 0 comes around, inverts and becomes a 1 and shifts back in. So if I do a shift, I'll get a 1 here, which means my 1 case looks like this. Then when I shift again, this one will move over, the zeros will move down, and the last 0 in line will get flipped and come back around. So this will be 2. Again, I do another shift to get to the next state, which is 3. The 2 1s move over. The zeros all move down, 0, 0. The last 0 comes and flips and comes back in. All right, so you can start to see the pattern. Last 0 comes around, becomes a 1. Or, of course, shifts down 1 more time. The last 1, 0 flipped and came as this 1. When I go to 5, this last 0 will flip and become a 1 and the others move in. I'm at all 1s. Now I've got a 1 that's going to get flipped. So when I go to 6, it will flip around and I'll get a 0. And then the 1s, 7, sure, all in view. 7, I'll get 0, 0, 1, 1, 1, 8, 0, 0, 0, 1, 1, 9, 0, 0, 0, 1. And then 10 comes back around, right, to all zeros. So this counts 0 to 9. I've got 5 registers. I've got 10 possible states out of it. So I basically end up with twice as many states as I had registers. So that makes a little bit more efficient than the ring counter. I get twice as many states out of it. It's not quite as easy to be able to decode the states. Remember, on the other one, I could just take the state out. But I have to take 2 bits to record what state it's at. And the 2 bits that we always check are wherever this 1 to 0 goes. So we can see right here, let me just label these again, right? A, B, C, D, E, just taking the names, right? And let me start with the 1 states. It'll be easy to see where they get them, and then we can talk about how we can check the other states. All right. If I've got a 1 here, which is A, so if A is on, but B is off, so A and B prime, that means this is a 1, this is a 0. There's no place where this is a 1 and that's a 0, and the rest of these aren't zeros. You can look at it. Every spot where this one's on, see the next one's on, next one's on, next one's on, next one's on. There's no others, right? So the only time I get this whole pattern is when it's 1, 0. And you can see, because it makes continuous blocks of the zeros and ones, all I have to do is find where the edge is, right? Where does it go from 1 to 0 or 0 to 1? So for all the ones when 1 is on the left-hand side, I just have to check. This is B and not C. That tells you that the boundary is there, which is only happens at state 2. If the boundary is here, that only happens at state 3, which is between C and D. So I want C to be high, but D not. If D is high and E is not, then I have to be in 4. Come back to 5 in a sec. If A is low, but B isn't, so the flip of this, right? Flip both of the inputs, but still an AND gate. You only see the lead 0 and the next one 1. The only time that happens is in this state, lead 0, right? So the only time you get that combo in the first 2 bits is here. So now I'm going to track the trailing edge. The zeros are coming in. So that's 7. This is 8, which is B prime C. 9 is between C and D. And that's 8. And then 9 happens when I'm between D and E. All right. That only leaves me these 2 because there's no transition. If the first one is 0 and the last one is 0, so A prime and E prime, the only time they're both 0 is in this case. You can find all the other ones, right? You can get A and B, and you can get A and C, and you can get A and D are 0 in other cases, but you only get A and E here. So A and D happens twice. A and C are both 0 in 3 locations. So, but A and E are only 0 only here. So that's the correct one here. Similarly, if I check if A is true and E is true, not their primes, so not A prime, E prime, but if I check AE, that only happens, right? They're both only 1, only on 6. So therefore, I can now check these. So now I have a single AND gate that I can use, and it taps 2 of them, and I can use that to now find the values inside of my Johnson counter. So we use these for the outputs. So this is the kind of state identification. Or uses these gates. All right, does that make sense? Okay. So I have to open the door. It's getting really hot and like I mentioned, this is actually Welcome to my laundry room. It's the only spot I had a nice wall and a little, I kind of have a laundry organizer unit I can rest my computer on here with enough light to do this. So that's a small room, so it's hotter than heck if I leave that door shut. Hopefully nobody walks through. Anyway, so that gives us our kind of setup for a Johnson counter. Again, Johnson counters are really nice if you want a fairly simple to decode state. Again, it's very hard for this to get errors. It's not as nice to read as the other ones, but it allows you with a lot less memory. So it doesn't gobble up huge amounts of memory cells, which is important on FPGAs because memory cells are pretty limited on FPGAs. So, this is kind of nicer for those things. So if you need ring-like behavior that's easy to decode, then a Johnson counter is the answer. And you just have to follow the edges. I would not memorize this. I just show you so that you can understand, follow the edges. And on the cases where it's not, you just take the extreme ends and check to see if they're both 1 or they're both 0. All right. If we feel good with Johnson counters, then we'll take a look at how we can handle a few other cases inside kind of more generic ones with binary counts. Okay. Now, we built binary counters last time. Now, what if I want something that's not a binary? Obviously, if I have n bits in my counter, right, and I'm doing a binary count, then I'm going to get 2 to the n states, which will be numbered from 0 up to 2 to the n minus 1. And that's the range of numbers I'm going to get. So often what we'll do is we'll try to kind of approximate these. And this is particularly with kind of larger counters, you're pretty much stuck with binary counts. So for instance, all of you have to do things like you've got a 50 megahertz clock and you maybe want to run something at 75 hertz or 50 hertz or something of that sort. Right? So, I could say, for instance, I need to go from 50 megahertz down to 50 hertz, and that's on the order of about 1 million. So ballpark, I have to count in the range of 1 million to be able to get this. And I could say, okay, well, how do I get millions? This is where we take advantage of some of the nice properties of binary numbers. I'm going to show you a couple of shortcuts that really help us with this. So 2 to the third is right around the number 10, right? It's the number 8 to be particular, right? 2 to the third equals 8, but we call this pretty close to 10 for our ballparking, right? And if we go up to 2 to the 10th, 2 to the 10th is equal to 1024, which is pretty close to 1,000. So this is what we call 1K. So every time we have something that's a multiple of 1,000, I know I need 10 bits basically. If I break things down into multiples of 10, I need at least 3 bits. So you'll see this as a slight underestimation. So we'll often on these ones, we'll calculate based on this, and then we'll add 1 extra bit in to account for the fact that we kind of undersized it. So for instance, 10 cubed, right, is 1,000. So I could say, okay, I need 3 of these, right, which is 9. Got to count 1 extra bit for safety because I was undersized. So that gives me 10, which is exactly what my approximation here is. So that's kind of why it basically ballpark works. Now I want 1 million, right? And a 1 million is equal to 1,000 times 1,000, which means it's 2 to the 10th times 2 to the 10th. Power of exponents tells me this is 2 to the 10 plus 10, which is 2 to the 20. So that tells me to count to 1,000,000, I need 20 bits. Right? So I can look at that and say, oh, to go from 50 megahertz to 50 hertz, I'm going to need somewhere in the ballpark of 20 bits. Okay? Now, I might need a number a little bit less than that, but you always want to overestimate. And this is why we're going to overestimate, because I'm going to count to here, and then we'll have some unused states, but I'll at least have enough states. And I will prevent the unused states from happening. So far, so good? Yes. Awesome. All right. So let's consider this. Now I've got 2 to the 20th, right? So 2 to the 20th, I've got over 1,000,000, right? I in particular have 1024 times 1024, right? So I've got over 1,000,000. So I want something less than that. I can now say, okay, I'm going to build a counter that's a 20-bit counter. How do I handle those unused states? So let's go through a couple different options that are here. And, well, actually, before I start listing options, let me open it up to all of you. What options do you see of how I can deal with these unused states? Anybody have any ideas? Set them to null. Yeah, that's a good idea, right? So I could check if I reach my max and then set it to 0. And set to null, or I'll just say clear it. Right? So I could check if I've actually hit the maximum number and clear it that same cycle in there. That would be one way I could do it. Tied into this, so I'm not sure which of these two you meant, but it gives us a couple options. So I can use the clear function, or if I can check to see if I'm just before the max, right? One less than the max, and I could then load a 0 on the next time slot, right? So remember, clear happens instantly, right? They're asynchronous. So I could see if it happens max, and the second it goes up, I just cut it off at the knees, right, and clear it out. That can cause a momentary glitch. It's pretty easy to build, and it relies on the asynchronous clear. It'll only be up for an instant, but it does provide a potential instantaneous thing. Some people will do this. The other way I can do is see if I'm one less. Remember, 2 to the n minus 1. I could check just before that, and then on the next state, I could tell it to load a 0 in. So either of those would count, from what Carlos suggested, to set them to null. I personally prefer this way. I don't like the glitches. It does work if it's what you've got available. It's really easy to do if you have an asynchronous clear. So if you're building independent components and it's not a high risk situation, so say for instance you wanted to have some kid's toy that was going to make noise or something like that, and you between, it says, "Hi, how are you?" Right? And it just plays that recording. After it says that, you don't want it to say, "I'm fine," right? Or something like that. You want to wait a little while. So they do that by putting a counter. And to make it kind of more human-like, they actually will set the maximum number to be a random value with a min and a max. Right? But it doesn't matter if it goes past it by 1, who cares, right? so it'll count up to that value and then check off. Right? So I could do either of these to clear them out. Can anybody think of another way? These are kind of big strategies. How about this one? What if I loaded my number, my max, that I want to start on, like 1,000,000 here, and counted down to 0? So I could load, technically speaking, my max -1, right? And then tell it to just count down, subtract 1 each time. And then I just watch for whenever it hits 0. When it hits 0, I stop, and you can either decide to reload the max, or maybe, you want to let it, I'm fine, how are you, type of a thing for a toy or whatever. You might want to have it do something else before you start the counter again. So you might want to load in a number and do a count down instead of starting at 0 and doing a count up. So that's another possibility. I'm trying to, at this first part, get you to open up your mind to alternatives. Okay? There's a lot of ways we can do counters. There's far more than we're going to be able to do here. I just want to do a few, start kind of thinking about some other options that are in here. So here's another option. Anybody think of another way I could go about doing this? Too soon after lunch, eh? Oh. Load and count up to, yeah, so I'm presuming what you're saying on that is, like, let's say I've got this, the 20-bit number, right? I could, for instance, I could load 2 to the n minus 1, the biggest number I can count up to, period, minus whatever my count max is, right? Whatever I want to count up to. This is total possible. That's the range I want. So this minus this is the unused states. So I can load, right, basically how many unused states do I have? And then I can count up. Maybe I'll just say all ones. Yeah, I can absolutely, do that type of a thing, right? Using that and going up. That's another way I could do them, right? Load in the unused states and then count up to all ones, which is related to this. You can either do it 2 to the n, minus your max minus 1. That gives you the same thing. But yeah, that's there's another way you could do it. There's tons of different ways. So anyway, this just gives us kind of 4 different ones off the top of the head. I'm going to talk probably mainly on this one, although we will briefly look at how you could build this one. As you go on, those are kind of a couple obvious ones. And if we want to, we can talk about how we can do these ones in more detail, but it gives you the basic idea. Basically, we're going to use either the load feature for most of these, or we're going to use the clear feature, to be able to get our value in. You can also just build one that's kind of like a regular running counter, and then you just look for that case and send the flag out to it, and they can reset when they want. That's another way, right? So just, build a binary, right, and send a flag when you reach the end, and then they can determine whether they want to clear it or not. That just makes an easy thing to build, because oftentimes we'll want to just keep reproducing a safe design. And that safe design might have a binary load to it. So when that flag comes out, I can just have it automatically have all zeros set up on the input. And when the flag comes in, I use that flag to go to the load command. Right? But I can also send that flag to other things as the clock pulse. It's another way I can do it. Right. Like I said, there are so many of these ways. When you start thinking about them, you'll start coming up with just dozens of minor little variants to them. The reason why we want to have a lot of different variants is, in any given situation, something will be easier to build, right? Easier, more reliable. The more alternatives you have, the more you can check them and see which one takes the least amount of time and gives me the best result, right? Least effort for best result is engineering efficiency. Right. We good with at least our brainstorming stage? So think about this heavily when you go into lab, right? I don't want you to make a complete disconnect between the course, even though they are really technically separate courses, but they're really meant to be very closely wound together. So when you're going in and doing the lab, right, try to, in your mind, brainstorm, how might I approach this? And then amongst those, see, okay, which one did they want to do? And then you can kind of use that to see how to build them. Because once you've kind of brainstormed them, it makes it a little easier to build. So now we've got kind of our ideas and we pick one. Let's say, for instance, we decide to do kind of the load a value in, right? So I'm going to have basically here then a binary counter which has a load feature, right? Maybe I should say with load. So I've got an output line that is my current count, and I've got an input line, which is my data load. And then I've got a command here for load, and I've got a clear. And even though clock is a control, we traditionally stick clock down here. So I've got a load, I've got a clear, and I've got a clock input. I've got a data I can load, and I'll do a count. I might also have up and down. That's some extra options. This would give me a pretty full-fledged setup that's on here of capabilities that can go on. So count, if I want to do everything, I could also potentially have an output that's a flag that I've reached something. But I'm going to ignore the flag, and I'm really only going to use the up count at the moment. So if I wanted to do a count up counter that counted to less than this amount, well, a few ways I could go about doing it. The down count, I would set to 0. Don't count down. The up count, I'm going to set to 1. Just count up. So I've inside here, I just have a built binary counter that's able to do that counting based on these signals. We can talk about how we can build this, but that's essentially what we built last time. A straightforward binary counter. It's got all the states. So when I tell it this means count up, never count down. Load means loaded a new value. clear, set it all to 0. This is asynchronous. And then I've got, of course, my clock impulse. I'm going to assume that I want to count this at my regular clock rate. So I'm going to hook this to my clock. Now, I want this when I have reached one less than whatever my max count is. And it's one less because I'm going to count up to 0 to max minus 1. That gives me a total of max numbers. So if I want exactly 1 million, then I'm going to set this to count from 0 to max minus 1. Now, the reality is when you're doing this for like the visual display part of it, it's not so precisely as a 1 million or whatever, right? You'll calculate a number, like you'll say, maybe I want 75 hertz or whatever, 50 hertz. That's what I want, right? And you'll calculate an exact number. If you're off 1 or 2 for a human display, your eye cannot count that small of a time unit. It cannot count, that single 50 megahertz clock. You just cannot see millions of a second. So it's not as precise on here. So I would, for those cases, pick whatever number is an easy number right in that zone to make your life work nicely. But let me assume that it is precise. I'm doing this for some physics experiment or something like that. So I need this number. Maybe it's a medical number, right? So I've got max minus 1 as a number, and I've stored this in a register. So this is just stored right at the very start that I'm going to count to. So I'm going to take these two numbers and I want to compare them. I want to see if they are similar. Now, for my counting range, I would generally assume that my count is less than max minus 1. Because if it's not, I should have already reset the dumb thing. Right? So I'm going to make that assumption. And there's a couple ways. This symbol right here, it kind of looks like your muck shape. But then I pull a notch out of it. That's an arithmetic logic unit. So what that means is it's some type of, it could be a general ALU or it could be a very specific thing. There's two different ones I could use here. Let me give you one type and then we'll talk about the other. I could do just what's called a comparator. A comparator we show by an equal sign, and that means it sees, are these two numbers the same? So if my count has reached max minus 1, it has reached the top number, the next number should be a 0. Right? This will send out a single bit. So this is, an n bit count. So this is n bits. This is an n bit load. It's going to send a single wire out, which is true, they're the same, or false, they're different. So I'm going to take that true signal and I'm going to hook it up to load. I'm going to assume at the moment that clear works on a high, so I'm going to set to 0, which I'll just put in parentheses, not clear. I'm not going to use clear at all for this setup. So what I do is I just have a normal binary counter that does not have a stop. It runs through all the states. The count comes out and I just check, has my count reached max minus 1? If it has, send me a signal that says it's reached it, and that'll be my load signal. And so the next clock cycle, it'll read the input, the data load. And I'm going to take that data load and I'll just hook it to all zeros. So that means it's going to count 0, 1, 2, 3, 4, 5, 6. It'll get all the way up to max minus 4, max minus 3, max minus 2, max minus 1. Each time, it's going to just normally count. That's all built into the regular binary counter we did last time. The second the output is the same as max minus 1, we'll just tell it, okay, don't go to the next number, just load this new number in for me. And it's hooked to all zeros. So it'll just load a 0. And now I can just, it'll automatically hit max -1 and it'll go right back to 0. So this was the second option that we had, right? Count from 0 up to max -1. And notice I didn't have to do anything different than I did last time. I can literally use my synchronous binary counter that we had. Right? If my synchronous binary counter doesn't have a load, all it is to add it in is to put a mux, right? It either gets the count +1 or we load a 0 in. And I'll show that here in a sec. But it's very easy to build this circuit. All I'm doing is configuring what we built last time. And this type of a reuse and just add functionality on top of a simple system, right? That's what we call bottom-up design or object-oriented design if you like computer science. So in computer science, you take simple classes and you build more complex classes off of these base classes, right? You polymorph them, you use inheritance, and you build more complex stuff. That's actually borrowed from this idea that's been used in hardware for ages and ages. And it just makes your life much simpler. Smaller units build bigger units. And since we can then test these units over and over again, we have a lot of confirmation that it's a safe, good design. All right. Do we feel good with this idea? Yes. Okay. So this is idea 2. Can anybody tell me how can I take this circuit and turn it into idea 1? Doesn't take a lot of change for it. Remember idea 1, instead of loading, we were going to do a clear. So how could I shift this idea instead of loading zeros, to clear to 0? Right? So I could use a mux and hook them over, but the clear is its own input, so I don't necessarily need a mux, but I could do it that way. Okay, I see a switch, the comparator output to clear. I would say don't load, and now the clear. And there's one more thing I have to do. So that is a correct step. That's half of it. Let's say I'm being like really anal retentive. I want this exact count. Put a 1 in. Now, so I'm not, since I just hooked load to 0, this is technically a don't care. It'll never get loaded. You don't even need to worry about it because the clear will take care of it. So I don't have to actually worry about that one. So this is going to compare to max -1. Right? And the second it hits max -1, it will instantly clear it. It won't wait to the next clock cycle. So what I have to do is instead of comparing it to max -1, I have to compare it to max. Because then the instant that max count hits max, it will then clear it and go to 0. So if you were looking at here's my clock pulses coming in. It doesn't have a bubble, so I'm measuring on the positive edge. So if count here, if it was
max minus 1. It'll go to the next one, it'll become max, right? And the second it becomes max, this happens. It's like a brief instant afterwards, it goes from max to 0. Because the asynchronous clear comes in and just knocks count out. And so the second that happens, then at the next clock pulse, it'll go to 1. Does that make sense? So to get that full count from max minus 1, we don't count this little tiny thing because it's like literally a fraction of a clock cycle. It's as fast as the electrons can go that clear. So it's usually pretty small. So I have to make that adjustment also. This one, like I said, is a little more dangerous because you do have that short uptime. If this is too slow of a circuit, it might be up for a little bit of a time, and that's not quite as good. But it is another way I can handle this circuit to take care of it. Like I said, sometimes you'll have a counter that doesn't have a load in, but it might have a clear. And so without having to modify the whole thing, this can actually happen. And as long as short glitches don't matter to you, then you're totally fine. Okay, good. Awesome. So that gives me another way to do it. Let's talk briefly about one of the ways I can kind of do this in a similar fashion, which would allow me to add in. We talked about building a very fine circuit to it. There's another way I can build this binary counter. So we'll talk about inside here a different way than we did last time. And then I owe you one more on how to build that circuit, not using a comparator. But let me do this one first. So inside on here, imagine I've got however many, n bits of my state. Okay? So I can take that, and with an arithmetic logic unit that does addition, I can put a 1 in on the other thing, 1 in as many binary digits as you need, right? This is equal to a whole bunch of zeros and then a 1. The output of this is going to be n bits that's 1 bigger than this. And I just run it in. So this technically is my next state logic. Right? So if this is my current state, this is now state plus 1. So my next state is state plus 1 because of this. And I just read it in. So this will technically just keep counting up every time there's a clock pulse. So it's a very easy way to build this type of a counter. Now let's say I wanted to have a parallel load. This is where I could put that mux in. I could say 0 is my normal run state. So I just take my next state, which is state plus 1, and I put it in 0. And then in 1, I can have my load data. And then the choice of this mux comes out. This is the load command. If it's a 1, it'll pull from load data. If it's a 0, it'll do regular addition. This is a very easy way to build that load command and functionality into that state. It's very simple. In terms of making a module in Verilog for this, right? A counter, with load. So I might want to be able to counter with load that's in, and I'm going to need to have several pieces of things that are input. I haven't shown it here, but I would need a input need clock, I need reset or clear, either one you want to call it. And I would need load, and I would need input, right, n -1 down to 0. That's load data. And then I need my, whatever you want to call it, state or count or whatever you want. That's an output. Right. So I could set up my module. I'll have two things. I'm going to need basically this state bits here, where I've got my state output. Actually, let me call this count. Because I like to do state completely internal. So depending on the version of Vivado, they sometimes let outputs be accessible, sometimes not. The standard is not to. So I would technically then have a reg n-1 down to 0, or and I'm assuming you substitute with your number or you set a parameter. I'm not going to sweat that right now. I'd have state and next state. And, that takes care of it. And then I would just assign count be equal to state. That just drives it so they're basically the same. It's making the names equivalent, but state is always viewable. And then I would just do always at, we'd have our pos edge clock. And in this case, I think I was doing positive the reset too. So pos edge of reset. Let me do RST because it'll fit on my line better. So always at pos edge clock and pos edge of reset. I would just see if reset is high, then state gets a 0. Else state gets next state. That puts essentially just does this kind of a hookup on. I'm going to actually just do that technically makes this wire next state here. So I technically need to have a state +1 or something, state P1. So I'd have to add that in here also, state P1. I'm going to do that up above. Is it okay if I erase this? Yes. Okay. So all I might have to do is build this wire. We'll add the mux for the selector for next state. We'll do this all in one fell swoop. So this is my combinational logic. That stuff's pretty standard, what we've done so far. Now always at star. Now what I want to do is build a case statement because I'm going to do my mux first because my mux is the closest one to next state. So I'm going to say case, and in this case, I only need to handle load which is one of my inputs, right? So case load, if it's a 1, then what I'm going to want to do for that is to actually do set my next state to be my load data. So next state gets the value of load data. And that is, again, another one of my inputs, right? So I just take, if you're telling me to load data will become my next state. Next time the clock pulse comes in, it reads it, and we're done. The default, which is 0 in this case, is to do my count, which is the adder. So at this point, I can either build that one. I technically don't need the state plus 1 for this implementation because I'm going to build it in. I'm going to say next state gets the value of state plus 1. And I literally just give it the plus 1. So now it's got a couple options. It can technically do an adder if it wants and add 1 to it. It could also build, since we do so many times we add 1, we actually built a special piece of hardware for this called an incrementer. And an incrementer just adds 1 to a number in binary. So it could also recognize this, go, oh, you're doing a plus 1, I can do an incrementer. The nice thing is that we actually have adders that are built into our system that are hardware adders, so they're very fast. So instead of building one, it'll often just take one of those hardware adders and just run your numbers through it. So you get a very quick response off it. So the output of this technically exists and is the state plus 1, but I never need to call it because I just combine it and send it over here. Right? And then I can just do my end case. Right? The always doesn't need to be ended because this is technically only one line. Just like this is an if statement, so it's technically only one line. So then I just have to end my module. And then I would actually have a nice counter that has a load built into it. And I could use this. So this is Verilog code that will work nicely to handle everything else. I really like making a very safe registers for them and then do a safe next state logic. That separation, while you don't have to, you can technically build them into it. I could make a complicated statement here that replaces next state, but it's not as pretty. You don't see it as well. It's harder to get the logic because everything becomes a special one-off. If you get very used to just building the registers and then doing the next state logic as a separate unit, you'll just tend to get less errors. And that's always a good thing. So this would build my counter. Do we feel good with this? Awesome. So this type of a thing is something you can do all day long inside of your lab areas. And that now gives you the box we had, which had, run those inside. It has my load data, and it's got a load command, and it's got a reset or clear, whichever you want to call it. It's got the clock automatically built into the registers, and it's got my state or count coming out. And in that case, I built it as an automatic up counter. All I'd have to do is make that mux a little bit bigger, and I could have a count up state and a count down state. And I would pick one of those as a default. And then you could have an up down count that tells you which way you're going. But right now, this gives me my basic up counter, which, like we said, we can then just put zeros on my load data. I would tend to use this, set clear to 0, and then put in your external load and nothing command max minus 1 as your selection data. And I said we could do this with an equal sign. But if you slightly alter this circuit, I'll show you why I want to slightly alter this. I can put a different one in here too. So max minus 1, I could still do the equal sign like this. It doesn't matter for checking if they're the same, which input you're putting them in. But I could also do this by minus, in which case max minus 1, which is larger, minus my count. Now, since max minus 1 is always bigger, I want on the first input. So it's always a good count if this number is bigger than that. So if this one is bigger than that, the difference will be some positive number, which will look like, 0, 0, 0, and then some combination of ones and zeros. Right? Okay. So you'll have something that looks like this, but your leading number will be 0. When they're exactly equal, they're all zeros. And when this one becomes bigger, then it all of a sudden becomes negative, which will have a whole bunch of ones. So this is when they're equal, and this is less, and this is greater than. Therefore, what we often will do for these is we'll check and see if the leading bit is 1, then that means the thing that I'm subtracting from my count is less than my total. The second they become equal, they're all zeros. The second it's greater than, it's all ones. Okay. I can take this equal here to test them. So it's actually going to output a full-size number here. So each is going to n bits. This is a full-size number. My 0 is all zeros. So I can take this into, I'm just going to draw a single OR here. And what this means is I take all n bits and I run into the OR. Now, if all of these bits are 0, then I'll get a 0. In any other case, whether it's less or it's greater, there'll be some ones, which means the output of this will be ones. Does that make sense? The output of this is an OR gate with n inputs, but a single output. So the only time I can get a 0 out of this OR gate is when they're equal. Right, so I'll get a 0 when they're equal. I'm going to then take this and I'll just invert it. And then I can hook that into low. Now in Verilog, this is really easy to do. This is easy to do because I just do subtraction. Remember, subtraction uses that adder hardware. So I could just do subtraction, your fixed number that you're looking for, max minus 1, minus n. And then I run it into this OR. Remember, OR looks like a vertical pipe. So if I said something like in Verilog A or B, that would, assuming these are both single wires, right? It would take, whatever A's value is and OR it with B's value. There's a slightly different version where I just say OR B, right? That's technically should be illegal logically, but if B has multiple bits, this has a special meaning. This is then called a reducing OR. And what that means is take all the bits of B and OR them together. So it's a shorthand notation for us. It just says, hey, this is a quick way you can reduce it down to get a single value out of it. And that's what we're doing here. So this is a very easy operation inside of it. So if I took the output of this subtraction and I reduced it, right? I can take this OR, put in parentheses, and I got a max minus 1, minus my count, and then I ORed it, that will do that subtraction and do a reducing OR, basically build that. And then I want to take this and I want to knot it. So I can build this whole thing right here just by this simple statement inside of Verilog. So this is just an alternative. Now, this is one way I could do it. The other way, remember, is doing a comparator. This is fairly simple to build, and it at least takes advantage of this subtractor. I'm assuming max minus 1, you just store that number. So you don't actually do that minus 1 subtraction. You've done it in advance. So this is using the subtraction version. The comparator is even easier to write. Max minus 1, and we just use the double equal. That's a comparator right there. Okay. So that's easier to write. The only advantage that this one gets is that you may or may not have a comparator circuit built into your system, so it might have to build this, and that could be more complicated. Whereas the adder subtractor might be built in, so you have very fast hardware to do it. So that's the only reason I would do this instead of this. Most of the time I would just do this. If time-wise I needed to save some time, I'd remember, oh, I might have a very fast adder subtractor that could take advantage to reduce time costs. All right. Any questions? Everybody's gone sleep on me. Nope. Okay. All right. Well, we are at our time. So we have talked through some ways that we can implement things inside of Verilog. We've looked at a couple ways that we can do counters that don't use all of their states. We built a few of them. We took a look at some trade-offs that we could do on these. And we talked about Ring and Johnson counters. So we got through basically all the fundamental counting routines we can use. And hopefully you know when you can use them and how you can use them. So if nobody has any questions, I will wish you all a good day. I'll give you a sec here. So any questions before we go? So the final will include everything across the whole semester, but it will put emphasis on after the midterm. So roughly speaking, I tend to do about, say, 2 to 3 times as much stuff on after the midterm as before. But I usually save, 1 or 2 type of questions on the earlier stuff, just to make sure people haven't completely ejected that knowledge. Plus, there's just going to be sometimes you might have to use a Carnot map to build something. So we've talked about other ways you could do it without Carnot maps, but that's because I'm assuming, build it with Carnot maps is always an available possibility to you. So for a small counter, if it's only like, 2 or 3 bits, it might make perfect sense to build a counter, not by doing kind of like one of these high level ways, maybe you actually do a Carnot map. So you get a more efficient small build instead of, right, an adder subtractor, it definitely works, but it's a fairly complicated circuit. A Carnot map could potentially get you a smaller one. Any other questions? Yes. So the final is still what, like two and some change weeks out. I mean, we have this week and next of classes, and then there's a couple study days and whatever. So I'll do the same thing I did last time. I'll give you a couple sample final things, and with solutions, and then I'll leave open some time where you can kind of ask me questions, and I'll record it doing one of these type of things. And we'll set that up based on whatever's convenient for all of you. I am torn. I'm not really super happy seeing, how my son has to use and others have had to use the Respondus things. I am actually contemplating allowing you to do the um, final as what would be called a take home, what I'd call an honor guard thing, um, because I'm not sure for when you're consulting notes and that, I'm worried that Respondus will just flag you for all kinds of stuff. Um, so I am somewhat tempted. I'm still debating this, whether I want to just give you the test and say, you know, I will collect this back tomorrow and you've got whatever time you want to finish it. So if people have strong feelings one way or another, let me know. Um, you know, and I'm that would be, if we go that way, it'll be a trust your honor thing, and I'll make you sign something that says you have been honorable and not cheated and that kind of stuff. But that I think is I'm leaning that way. Any other questions? All right, seeing no other questions, I wish you all a great day and hope things go well. And if you need problems with either class or lab, let me know. God bless you all. Miss you.